In lecture 17a, we're going to consider one of my favorite topics in differential equations, and that is the flow of a vector field. And we're going to look at some pretty cool animations at the end of this lecture to show you, to illustrate the main ideas. The flow of the vector field will be considered for a partially decoupled linear system, but also for a partially decoupled nonlinear system. And there the formulas get pretty crazy. We're going to rely on Mathematica, not just to make the pictures, but also to do the solving for us. In the first part with the linear system, we'll also talk more about the matrix exponential, which I introduced in lecture 16a. You can see lecture 17b is the linear algebra portion, abstract vector space theory, real intense kind of content right there. Something a little strange with lecture 17a and 17b is the smartboard's not working like it usually does. I can't use the pen for some reason, and I don't know how to fix it. All the IT people have left for the day, and so they can't help me. Hopefully before lecture 18a and 18b we'll be able to get it fixed. All right, let's get into details of solving a partially decoupled linear system. We're going to take a particular example this time. Consider the following first order linear partially decoupled ODE, ordinary differential equation. It's going to be a vector differential equation. You can think of it as a system of equations or one vector equation. As a vector, y is the vector whose components are little x and little y. Its derivative with respect to t consists of a vector whose components are dx dt and dy dt. It's a linear system, therefore it's a matrix times the vector y. The matrix that I picked is this particular one right here. Here's the vector boldface y, and if you go ahead and multiply that matrix times this vector, you get this. You should double check all that. This is a linear system. Moreover, it is a partially decoupled linear system. Why? Well, if you look at the dy dt equation, it only involves y itself on the right-hand side, no x's. It doesn't interact with x as far as its rate of change goes at all. We can easily solve that second equation, dy dt equals 3y, to say y is y sub 0, the initial value, times e to the 3t. Okay? Then we can use that to find dx dt. Here are the details. We're going to find a unique solution of a generic IDP, meaning for particular initial condition that I'm going to label x0, y0. Again, using the fact that it's a partially decoupled system, the matrix in question right here is what's called upper triangular. Below the main diagonal, you have all zeros. In this case, just one spot below the main diagonal. It's a 0. It's this triangle up here in the upper right portion that consists of the possibly non-zero numbers. In this case, they're all non-zero. All right, so again, the dy dt equation is 3y. We could separate variables, but we don't need to. Just go ahead and use the knowledge we have already. Y will be y sub 0 times e to the 3t. Now substitute that back into the dx dt equation. dx dt is x plus 2y. Replace the y right there with y0 e to the 3t. I'm going to go ahead and use the method of integrating factors, so I'm going to subtract x from both sides and write the equation as dx dt minus x equals 2y, which is 2y0 e to the 3t. Use the method of integrating factors. The integrating factor is going to be mu equals e to the integral of the coefficient of x on the left-hand side there, which is -1. That simplifies to e to the negative t. You don't need to add a plus c. You can essentially just take the c to be 0 there. All right. Using that integrating factor, what you do is you multiply both sides of this differential equation by the integrating factor. That's why it's called a factor. When you do so, on the left side you get e to the negative t times dx dt minus e to the negative t times x. When I multiply that part right there times e to the negative t, and when I multiply e to the negative t on the right-hand side, the e to the 3t and the e to the negative t combine to give you an e to the 2t. The thing that's special about integrating factors is the left-hand side now is the derivative of the integrating factor times the unknown function. X is a function of t here. I'm just not making it explicit. You can always double-check this with the product rule. The derivative of this product is the first function, e to the negative t, times the derivative of the second, dx dt, plus the second x times the derivative of the first. And the derivative of the first, e to the negative t, is negative e to the negative t. Because of that, you can integrate the left-hand side easily just to get e to the negative t times x. The integral of the right-hand side is not too hard either. You're going to get y0 e to the 2t. Now you do want to add a plus c, because we want to solve an initial value problem. Here is the general solution that I can obtain after now multiplying both sides by e to the t. X is y0 e to the 3t plus the constant times e to the t. Use your initial condition. X sub 0 equals x of 0. Plug in t equals 0. e to the 0 is 1. You get y0 plus c. Now subtract y0 from both sides. C must be x0 minus y0. And now I can plug that back into the equation that I got for x right over here in place of c. So x is this. All right? As a solution of the system, you want to put x and y together essentially as a vector, like this. Ignore this one this part for the moment. Just focus on the rest. Y is this vector-valued function of t. Again, think of x0 and y0 as fixed. This is really a parametric curve that traces out a curve as t increases in the plane, in the phase plane, the xy phase plane. As I often do, I wrote this as a linear combination of two linearly independent functions. And based on the definition of matrix times a vector, this can be written as this matrix times this vector. And in the last lecture, 16a, I said this matrix is called the matrix exponential for this particular matrix A right there, and it equals that matrix. And notationally, I can write it like this. Actually, in the last lecture, 16a, I wrote it like this, with the t after the a. It is a bit more traditional to actually put the t in front of the a, because usually when we multiply a scalar times a matrix, we usually put the scalar on the left. This does mean take t times every element of a to get a matrix. T times a is a matrix. And somehow I'm raising e to that matrix power. And I'm saying the answer is this. I'm not saying why that happens. Okay? Just that it's a good idea to call it that. In coming lectures, we will see why that works, at least for simple examples. It does get kind of complicated when your examples get more complicated. Let's look at the phase plane, as we've always been doing recently, of this particular partially decoupled linear system. The vector field, first of all, is the following function I'm going to show you. It's the right-hand side. It's a times capital boldface y. It is, if you want to think of it as such, a linear transformation. However, we're not viewing it as a mapping in this context. We're viewing it as a vector field. Here it is. I could write boldface f of boldface y is a times boldface y is this. If I want to think of boldface y as a column vector, as the input of the vector field, I can write little x, little y right there. This is just a function which takes two-dimensional inputs for y and gives you two-dimensional outputs. It's a linear function. It's really a linear transformation from R2 to itself, if you like. But again, unlike the linear algebra portion of the class, we're not viewing it as a mapping. We're not thinking about how points in the domain get mapped to points in the codomain, geometrically in terms of reflections and rotations and so forth. We're thinking of the outputs as being vectors that we attach to points in the plane. I'll show you the picture here and we'll talk about that some more. Again, the unique solution is this. I forgot to mention, what is this notation? This is my notation to emphasize that the solution is a function of t, calling it capital Phi. For scalar equations, I use a lowercase phi. The subscript here is boldface y sub 0. That is the initial point, the initial condition as a vector or as a point. When you plug in t equals 0, you get y0 times 1 plus x0 minus y0 times 1. E to the 0 is 1. The y0's cancel, you're left with x0. When you plug in t equals 0 down here, e to the 0 is again 1, you get y0. It does satisfy the initial condition. And you can also verify it satisfies the differential equation. Here's the phase plane with, as usual, the direction field. I'm not drawing the actual vector field itself because it gets too messy. So I had Mathematica draw the direction field that shows all the vectors having the same length, essentially. The true vector field would have different lengths for the vectors in the vector field. We'll see the Nullclines. And the flow, I'm calling it, related to the flow that I mentioned at the beginning of the lecture, that is made with stream plot. And we see that the origin is a source. Just confirm in your mind that this seems right. Let's focus on, first of all, the Nullclines. The y Nullcline is where dy dt equals 0. dy dt was 3y. That equals 0 when y is 0. In other words, along the x-axis. So along the x-axis, vectors in the vector field and the direction field are horizontal. They have 0 y component. And you can see that here. You can see along this x-axis, which I've also labeled brown because it is the x Nullcline, Solutions, well, they don't look like they're exactly on it. That's because Mathematica is picking initial conditions that are not exactly on it, but they're close to being exactly on it, like that blue arrow right there is close to being on it, exactly on it, and this one over here. That is what I called in the last lecture a straight line solution in both directions. The point is certainly a source in the x direction. But it's a source everywhere in 2 dimensions as well. That's related to the fact that the powers of E here are positive powers, positive numbers times t in the powers of the E's. That's related to why it's a source. What about the x nullcline? That's where dx dt is 0. X plus 2y equals 0. X plus 2y equaling 0 is equivalent to 2y equaling a negative x, which is equivalent to y equaling negative 1/2 x. Along the line through the origin, with a slope of negative 1/2, dx dt is 0 for solutions as they cross that line. There's 0 horizontal component. The vectors point straight up or point straight down. Solutions cross with vertical tangents. Going upward over here by this green line. This green line is y equals negative 1/2 x. And going downward over here. Why do I have both red and blue arrows in here? Well, look closely at them. The red arrows are all straight. They are the direction field. The blue arrows are not all straight. Some of them look kind of straight, but they're not all straight. You can see some curvature over here and over here, for example. Those are supposed to represent the solution curves themselves, the parametric curves defined by this formula. Anytime one of those curves passes through the base of one of the red vectors, like, oh, it's close to it right there, that red vector is tangent to the curve there. Okay? So the origin is a source. Now we're going to change our perspective. We're going to view this generic solution not as a function of t, but as a function of the initial condition of y0. Can we do such a thing? It is often useful to change our perspective about the unique solution of the generic IDP. Here's the formula again. I've shown this on 3 slides. Instead of viewing t as the variable, view y0. The initial condition is a variable. But wait a minute, I thought y0 is fixed. Well, whether something's fixed or a variable is all in your head. Okay, it's all in how you're thinking about it. So I certainly could think of y0 as a variable if I wanted to, and I could think of t as fixed if I wanted to. In doing so, we have the of t here. We should probably change our notation. We should have an of y0, I guess. So should I put the t down there? I choose not to. I also, for emphasis, choose to use a different version of the Greek letter phi. I've used lowercase phi, I've used capital phi. Now I'm going to use curvy phi. It's one of my favorite Greek letters. Right there, isn't that beautiful? That's one of my favorite Greek letters right there. And I chose to put the t up here as a superscript. Why? Because we will see that it kind of acts like an exponent. It's not an exponent, but it kind of acts like one. These phi t functions, when you compose them, you essentially add the exponents, as if they were actual exponents, even though they're not. There are exponents as part of the e's in the formula, but they're not literal exponents for this function. I'm not raising this function to a power. So again, all I've done here is change my perspective. Same formula in both cases. Here I'm thinking of y0 is fixed and t is a variable, and I get a parametric curve. Here I'm thinking of t is fixed and y0 is a variable. Do I get a parametric curve? No, I actually get a linear transformation. Think of t as fixed. This is a fixed matrix times a variable vector. Fixed matrix times variable vector is a linear transformation. Like in the lecture B's, more connections. We're happy for connections. Okay, is this a big deal? Why would I want to do this? When we take this perspective, first of all, some terminology. For any fixed value of t, like I just said, this function is a linear transformation from the plane to itself. I can write phi t as a domain R2 and a codomain R2. And I could ask questions like, what's the kernel, what is it onto, and that kind of thing. For any fixed value of t, such a function is called a flow map. For any fixed value of t, though I will tell you the most common value of t to pick is a 1. but you can really pick any value of t that you want. Furthermore, the family of all the flow maps, all these functions for all values of t, that's a family of functions, a collection of functions, that has a shorter name, it's just called the flow. It is interesting to see, and we're going to see this at the end of this lecture in Mathematica with an animation, how images of sets in the plane changes t changes. So I'm thinking of a given set in the plane. In the animation, S is going to be actually the unit disk, which is the unit circle and everything inside of it. And I could find the image of that set under this linear transformation. Does it rotate? Does it dilate? Does it reflect? We'll have to wait and see. And we'll see how it changes as t changes, and we'll make an animation for that. Here's another connection to linear algebra. In fact, since the determinant of this matrix exponential, this thing right here, which is a triangular matrix, is the product of the numbers on the main diagonal. Remember, determinants of triangular matrices are the products of the numbers on the main diagonal. We have a determinant of e to the t equals e to the t times e to the 3t. Multiply these things, which is e to the 4t. And therefore, for our example, we can say that the area of the image of S under phi t is, this flow map, is e to the 4t times the area of S. And so, for example, if t is 1, the area of S gets multiplied by e to the 4th. What is that e to the 4th? I don't know, somewhere in the 20s, 30s, 40s, or 50s or something. The area becomes that much bigger under that flow mapping when t is 1. We'll actually use a smaller value of t, and we'll see what happens. Now let's try the same kind of thing, except for a nonlinear system. Don't try this without technology, the one I'm going to show you here. I definitely did not want to try it without technology. I used Mathematica. You know, mostly I used Mathematica for visualizing things, but here it was definitely helpful symbolically as well to solve the differential equation. It's a partially decoupled nonlinear system. And you can find a formula, though it's insanely complicated. dy dt equals, I don't have a times y here, there's no matrix. It's just f of y, where f is the vector field, and an input y, and I'm saying the components of the vector field are little x minus little y and cosine of y. Could we still think about nullclines and equilibrium points? Yeah, and by the way, I forgot to mention where the nullclines cross, the distinct nullclines, you have an equilibrium point. We had a big black dot at the origin in the last example. What about the x nullclines here? It's where dx dt is 0, where x minus y is 0, which means y equals x. The line of slope 1 through the origin is the x nullcline. And remember, the x nullcline is where dx dt is 0, solutions are vertical, pointing straight up or pointing straight down. What about the y nullcline? It's where cosine of y is 0. Which happens where? Infinitely many places. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, etc. Also, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2, etc. Those are going to be a bunch of horizontal lines at these values of y. And all those horizontal lines are going to cross the x nullcline, y equals x, somewhere. In fact, the coordinates of the crossing points are going to be the same. For example, one will be pi over 2, comma pi over 2. Another one will be 3 pi over 2, comma 3 pi over 2. Negative pi over 2, comma negative pi over 2. Negative 3 pi over 2, comma negative 3 pi over 2. I'll show you the faceplane here in a second. Here it is. Isn't that beautiful? Wow. That is so beautiful. And it goes on forever, okay? There's infinitely many equilibrium points where green and brown intersect. All these black dots. And look at the flow. The red vectors are the direction field. They're all straight. The blue arrows they're curved are really the solution curves themselves. The x nullcline is the green one. That's where solutions cross with vertical tangents. Right there, and down here. And the brown lines are the y nullclines. The solutions are horizontal. The velocity vectors of solution curves have 0 y component. They are pointing to the left or pointing to the right. And where green and brown intersect, you have equilibrium points. And look at this. That equilibrium point is a beautiful looking source. This one's another source. That one's a source. And in between you have, what are these? Like right there and right there and right there. Well, there's nodes. Well, in higher dimensions we call them saddle points. There's a good reason for that, related to actual saddles that you put on horses. I won't get into it right now. There is a good reason for that. What a beautiful picture. Can we solve this system? I think with enough time I could do it, but it was nasty. Okay? Let's just show you what happens. The dy dt equation, dy dt equals cosine of y, is separable. You could divide both sides by cosine of y and quote unquote multiply both sides by dt, but it's quite difficult to solve, though it is possible. So there we have it, dy dt is cosine of y. And this, by the way, is the fact that it's partially decoupled, is the dy dt right-hand side doesn't involve x at all. So we can focus on that first. Divide both sides by cosine of y is the same as multiplying both sides by secant of y, because secant of y is 1 divided by cosine of y. So I get the integral of secant of y dy is the integral of dt, which is t plus c1. But then I have to do the integral of secant of y. And if you've ever done the integral of secant of y before, you know it's not easy. There are some tricks, but they're really tricky tricks to help you do it. What is that integral? It does involve logarithms. There's a little hint. It seems really hard. It's easier to integrate secant squared because it's just tangent of secant squared. Integral of secant squared y would be tangent of y plus c. That's easier. Integrating just a plain secant of y is harder though. It is doable though. This says doable. You can do it, but it's quite tricky. And even after you've done it, to solve for y as a function of t is also quite tricky. I'll show you how Mathematica did it. But I'm also just on the PowerPoint here just going to show you the answers. You ready? According to Mathematica, this is how y is a function of t for fixed y0. Or maybe I want to think of t as fixed and y0 is a variable. Well, not quite yet. Whoa! Y is 2 times inverse tangent, also called arctangent, of, what's this? Is that h a typo? No, it's not a typo. This is tanh, which stands for hyperbolic tangent. Look it up. So that's 2 times inverse tangent of hyperbolic tangent of this quantity, 1/2 t plus inverse hyperbolic tangent of tangent of y0 over 2. Whoa! Amazing. That is what Mathematica gave me as the answer. That is quite a composition of functions there. Hyperbolic tangent, just to give you a little insight into it, is actually related to exponential functions, and inverse hyperbolic tangent is actually related to logarithms. This notation kind of hides that relationship there. Actually, you might say this formula is not perfect. For example, we know the tangent function is undefined, for example, at pi over 2. It's got a vertical asymptote there. So actually, if y0 is pi, you get tangent of pi over 2, which is undefined. So this solution is limited in some ways, but it's good enough for our purposes for this lecture. Okay, this can then be plugged into the dx dt equation. dy dt was cosine of y. Dx dt equation was actually linear, but it involved both x and y. Go back there, show you. Dx dt was x minus y. What do you get? Here's what you get. Replace the y with this 2 times inverse tangent of hyperbolic tangent of 1/2 t plus inverse hyperbolic tangent of tangent of y0 over 2 in place of y. And that's actually a linear, non-homogeneous differential equation that could be solved by integrating factor or undetermined coefficients. Ha ha ha! I wouldn't want to do it. Finding the integrating factor or finding the general solution of the corresponding homogeneous equation would be easy. But guessing a particular solution of the non-homogeneous equation would be, I don't know how to guess that. And also, if you use the integrating factor and multiply both sides by the integrating factor, integrating the right-hand side would be, I don't know how to do it. But, amazingly, Mathematica can do it. I tried. It worked. Though there might be some limitations, just like there were some limitations up here. I didn't get into thinking about what those limitations might be. Are you ready? The answer is the most beautiful function you've ever seen in your life. Whoa! Involving a bunch of inverse tangents and inverse hyperbolic tangents in lots of weird ways. Natural log. Hey, here's a simple part of the formula. x0 e to the t, that's certainly a simple part, but everything else is a mess. That's what Mathematica produced, assuming I typed it correctly. There could be typos. I double-checked it, but whoa! Wow! I'll show you what I did in Mathematica to produce this. Huh. So I guess, putting all this together, we could write this. Think of y0 as fixed, meaning little x0, little y0 are fixed. Think of this as a function of t. What's in red is the first component, what's in blue is the second component. This would be a parametric curve for fixed y0 and x0, function of t that, if you graphed it, would be a curve in the plane. One of the curves in that slope field, or that vector field that I showed you, the phase plane. And I also could change my perspective and think of it as a flow map. For a fixed value of t, think of it as a function of boldface y0, which means it's also a function of unboldface little x0 and little y0 when t is fixed. Although it's no longer a linear transformation of y0, it's a nonlinear transformation now. This is a family of nonlinear maps, not linear maps, not linear transformations. Its behavior is much more complicated. But conceptually speaking, it's still similar. For each fixed t, we could call this a flow map. And the entire family, this is still a family of functions, one function for each of the infinitely many possible choices for t. That entire family is called the flow. You can look these things up, by the way, online. You can look up mathematical flow or flow map and that kind of thing to see stuff like this. How does this affect area? It's not so clear. We would need multivariable calculus. That determinant fact only worked because the linear transformation with the linear example was linear. This is a nonlinear transformation. For a particular value of t, like t equals 1, if you wanted to look at the area of the image of some set, you'd have to use multivariable calculus. You'd have to use double integrals, really, and you'd have to use a change of variables and something called the Jacobian determinant, if you've heard of those things. And the calculations, for all I know, would be just an absolute nightmare. But maybe we could approximate it and that kind of thing. That's actually the end of the slide content for lecture A here. Let's look at Mathematica now. This is a shorter lecture than most, and I'll try to keep the Mathematica fairly short as well. So this is the partially decoupled linear system example here. Here's where I entered the matrix A. Here I'm using dsolve value to solve the linear system. This is the solution. As a function of t, it's a parametric curve. As a function of x0 and y0, it's a linear transformation when t is fixed. Here is the matrix exponential. To confirm this, MatrixExp in Mathematica will compute a matrix exponential of this matrix t times a, which is another matrix. This is a matrix here, not a vector. 2 by 2 matrix. If I multiply it with a dot here times the initial condition vector, I do get a vector that is the same as this. These two things are the same, just confirming. Okay? So MatrixExp times the vector is really giving you the solution. Here I'm entering it as a vector field, and here I'm making the phase plane that you saw on the slide. I'll let you look over that code if you'd like. Contour plot, vector plot, stream plot are all used. List plot to make a big dot at the origin. There it is. And here I am defining the flow, each individual flow map. I tried making the t a superscript of this curvy phi there, up and to the right of it, but it didn't work because Mathematica wanted to think of it as a power. So I actually put the t above, straight above the phi there. As far as Mathematica is concerned, that's a variable, even though when we think about these things, we think of t as fixed. Although the animation is going to be as t changes. Yeah, there's what it looks like. It's just a different way of viewing it. Now I'm showing the phase plane from the previous picture with the parametric plot. And what this is going to show, if you think about it here, what happens when t is 0? This phi 0, the flow when t is 0, is actually the identity function. And so essentially, when t is 0, we're going to graph this parametric surface in the plane. U cos v and comma u sine v, that actually graphs the unit disk. U is the radius, where the radius varies from 0 to 1, and v is the angle, where the angle varies from 0 to 2 pi. We're going to see in parametric plot, not a curve, but a disk. And then I let t change. This is a manipulate. So I've got an animation parameter here, that's t. I'm going to let it go from 0 to 0.2. All right, so here is the phase plane along with the unit disk. Circle of radius 1 centered at the origin and everything inside of it. What happens as I let t vary? We see images of this disk under the different linear transformations phi t. But t is changing, so we see different images. And it is like a flow. Kind of seems like maybe a bad application, but maybe you imagine this as an oil spill, and the blue curves that you see, the solution curves, represent the paths of water molecules and I guess oil molecules. And we see the oil slick expanding over time, following the flow. The disk becomes an oval, an ellipse, and what's inside the ellipse. I'm letting t go up to 0.2 here. Remember that I said the area got multiplied by e to the 4t, e to the 4 times 0.2? 4 times 0.2 is about 2.2255. In other words, the area of this ellipse should be about 2.2255 or whatever it was times the area of the circle. Now the area of the circle is pi r squared. Pi times 1 squared is pi, about 3.14. The area, let's just pretend this is an ellipse, and it is actually because it's a linear transformation. Linear transformations map disks centered at the origin to ellipses centered at the origin. The area of an ellipse is pi times what's called the semi-major axis, which is the distance between the center of the ellipse and the farthest point, times what's called the semi-minor axis, which is the distance between the center of the ellipse and the nearest point. If you ballpark it, the nearest point looks like it's maybe about 1.2 units away, 1.2, and the farthest point looks like maybe it's 1.9 units away or something. 1.2 times 1.9 times pi is 2.28 times pi is about 7.16. You can try that. 1.2 times 1.9 times pi is about 7.16. And that, if you divide it by pi, is about it comes out to 2.28 times, 2.28, which is meaning this is 2.28 times the area of the original disk, approximately, which is close to e to the 0.8. 2.23 instead of 2.28. We're close. I was just ballparking the area. I was ballparking the semi-major axis and semi-minor axis. What about the partially decoupled nonlinear system? Mathematica could do it. I could solve this, and I got that. Again, this solution is not perfect because, again, some y zeros would be undefined. And I plugged that back into the dx dt equation and got this. And then through the magic of copy and paste, I just copied and pasted this whole thing down here into the first component of the flow map for a given value of t, and the second component was y. And I entered this, and here's the vector field, and here's the phase plane. There's that picture, and yes, I can now also make an animation. And this is the cool one, really cool one. I picked the unit disk again. Now watch what happens As time goes by, it doesn't get mapped to an oval, it gets mapped to some sort of elongated semi-oval, I don't know what else to call that, some sort of elongated egg shape under the flow. So the oil slick, if the blue curves were paths of water molecules or any molecule in the stream, in this, say, thin sheet of fluid, then the oil slick would look like that. Okay, I think that's really cool. So I hope you liked it. Thanks for watching.